Welcome, everyone. So last week we started talking about this um, visual autoregressive model, and the motivation being that we have the new image generation capabilities in ChatGPT, and so this is a technology that we think may be behind this. So we got to this last week, just the basic idea in terms of we're going to represent low scale images with fewer patches and high resolution images with more patches. And we're going to use a GPT-2 like LLM that'll do next token prediction. But we're going to be predicting the next scale of image, which, if we're predicting an 8 by 8, it means we're actually doing 64 tokens all at once in parallel instead of doing them 64 individual steps. So I'm pretty sure that's where we got to. And so the plan is then to continue, finish off this, and then we can have a little bit of discussion if we have time at the end about why this technique might be different from other techniques and why it might allow for some of the capabilities that we see in ChatGPT.
Sounds good. Do you want me to hit the play, Ted?
Please do.
Okay.
That's in the paper. Basically, what you're going to see is they're going to say for 1 to K, in this case, K was 10, okay? Like I said, they start 1, 2, 3, 4, 5, 6, and then they skip some numbers and they get up to 16 by 16. But you're going to start with your 1 by 1, and then later on, when you build your 2 by 2, you have to already have had the 1 by 1 because you're subtracting that from your raw image. And then you subtract the 2 by 2 from that result, and you keep subtracting and subtracting. And so if you think about like XGBoost or something like that, this is sort of a similar operation where you just keep trying to refine on whatever you missed in your earlier steps. So the training is you train the multi-scale VQVAE to be able to reconstruct images. So it's how does it quantize? How does the encoder, I think, is a frozen CNN, so that part's not trained. But the decoder, I think, does need to be learned. But anyway, you train this, and then this guy is frozen. So when you actually start doing your transformer training, your GPT-2 model, this part is not learning. This part is already
I don't even know how to
fixed.
spell your fucking name.
Say,
Fucking
here's my
dumbass
best
name.
shot at how to compress images and whatnot. And so then you can see here, I don't think this is a great diagram, but down here we have the blockwise causal mask. It has this sliding window that we talked about, and as usual in papers, neither of the axes are labeled. But so what we're simply going to say is I'm going to give you the 1 by 1, predict me the 2 by 2. I'm going to give you the 1 by 1 and the 2 by 2, predict me the 3 by 3. I'm going to give you those three, now predict the 4 by 4. And that training basically works just the same way as GPT-2. You just have an error based on every next token prediction. It's just that now we're predicting tokens in batches instead of one at a time. So there's only 10 inference steps to go from nothing to the full 16 by 16, which gets sent to the decoder. Okay. And this is in contrast to, it would be 256 inference steps if you did the raster scan thing. So then when you want to generate an image, so anytime you use these architectures like VAE, you throw away the encoder once you're done. It was useful for you, but it's not used for generation. So they did ImageNet. You give it what the class you want. I want a dog. Okay. And from that, it predicts the 1 by 1. It's one token. And then it predicts the 4 by 4. And it keeps repeating 10 times until it predicts the 16 by 16. You're iteratively summing these as you go. And so your grand total sum of all 10 of these predictions then gets sent to the decoder, and it spits out your pixels. And now you have your 256 by 256 ImageNet image. So that's the process. The results here basically are really, really good. And if you look at the paper, you can see the details, but not only do they have really good scores for image quality, but then also on the right, they say, if the amount of time it takes our big model to output an image is normalized to just 1, then how many times faster or slower? So you can see this model took 168 times longer to output an image, and it was worse. So yeah, yes, we have state-of-the-art results. Every paper has state-of-the-art results. But in this case, I think that they don't seem so cherry-picked, we can probably believe. We had a conversation about scaling and whatnot, so there's some things in here. I'm not going to go into the details, but at least up to the size that they built, which is not that big yet, the model seems to scale well, and it seems to follow this power law. So the hope is that it doesn't hit a glass ceiling. And so on this chart, you can see, for example, the DIT model, it got bigger. So it worked really well when they made it bigger from size 1 to size 2. And it worked really well when they went to size 3. And then they made it bigger, size 4 and 5, and it just didn't really help. That's the phenomenon that we hope to avoid when we have the right inductive bias that's not adding or subtracting anything from the core, data problem in and of itself. All right, so here's some sample images, and if you look in the paper, you can see that they show within each block, it's left to right earlier in the training before the model was very good. You get some really lousy images and weird artifacts, and then it gets better. And then also as you scale up into the bigger models, you get better and better. And so clearly this bottom right image is got a lot more detail and whatnot, and at least the right number of fingers, the right number of necks, that sort of a thing. All right, so I'm going to wrap things up here and try and save time for the R1 discussion for everything else. But it's fast, generates high quality images. Hopefully we have the right inductive bias. Code's available. You can play around with this. And there's already another paper, an Infinity paper, where they did text conditional. So you can actually say, I want whatever, an astronaut riding a horse, and it'll generate that for you. They also have some other things. I haven't deep read the Infinity paper. So I think this is interesting, and I like the fact that, again, that they didn't just try and copy an LLM, that they broke some rules. And one of the big ones is predicting multiple tokens at once. I think the idea that you can apply more information density to some things than others is an idea that, in my opinion, is going to pan out. Certain recent papers like the Meta, whatever it was called, Byte, whatever encoding paper, my understanding of the thesis of that is that not all words, not all tokens have the same amount of information content. And so they let this byte encoder kind of decide, when do I have a mouthful and I'm going to actually send that to the LLM. I think the simplest way to think about it is we use a form of byte-pair encoding in order to create our vocabulary. Byte-pair encoding was invented for compression, for signal transmission. And so the whole idea of byte-pair encoding is that we have shorter signal representations for really common words like the, and we have really long, expensive representations for words that get used super rarely, whatever, supercalifragilisticexpialidocious, right? And we took that technology, and each takes the exact amount of space in an LLM because they each get exactly one token that is the same dimensionality. So maybe we can find a way to be more efficient. Maybe it's like the Byte paper, but maybe we can actually say, oh, you're doing some math here, or you're doing some medical thing, and I'm going to somehow give you more information density here. But when you say the tall guy, like maybe you just don't need as many bytes and tokens in order to represent that information. And that might then allow the LLM to focus its computation energy where it really needs to, and not really spend theoretically as much energy processing the as some other word. Final note, the paper I did find to be a little bit hard to read because of all the notation. So I do have actually in the appendix just a little cheat sheet here for if you want to go through, like, an image is a three-dimensional object that has pixel values, height, width, channel, 3 channels, and all the values are I don't know if they are, but typically they're like floating point numbers between 0 and 1. And then you can see that like as it goes through the embedding, it becomes a 16 by 16, and then it goes through the code book, and then these become integers based on the code book size and so on. So if that helps anybody who wants to read more about the paper, this isn't going to explain everything, but it is just a little bit of a cheat sheet for all the different notation that they have in the paper. Yeah.
Is it too far-fetched to say something like basically that the conclusion from this paper in a way is that the understanding the fundamentals of LLM can basically help us have the same performance level without necessarily having all the bells and whistles, because in this case they're kind of connecting it with GPT-2, and so basically demonstrating that thinking deeper on the fundamentals of how LLMs will operate can also help us, or is that far-fetched to say?
Yeah. I think in terms of the fundamentals of LLM, we have this conditional probability where you say the next word depends on all the previous words that you've said. And it would appear just by experimental demonstration that that's enough. That like you can imagine, and this would be even more true in another language like German, where you have concepts in your head and you're just holding them and you're waiting, and then they come at the end of the sentence, right? So you sort of need like a stack or whatever that you're like maintaining as you're spitting out words. LLMs don't have a stack. They literally just say, here are all the words that I've already seen. I think in English, this works better. There's not that many times when you know a word you want to say, but you just have to stick a bunch of other words in there first, But like I said, I think in German, there's times when, what is it? Like the verb comes and the noun comes way at the end of the sentence or something like that, right? So you know that you want the subject to be the boy, but you just say blah, 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 the boy at the very end, right? But anyway, so yes. So the idea is, if we're going to extend the power of these LLM architectures, really the stackable transformer architecture, then let's find out what the right conditional probability that we should be basing it on.
I think I might have gotten it wrong, and it's the verb that comes at
Cool.
the end in German, but I think the idea is the same regardless of which word it is that comes at the end of the sentence. Patrick, I think you know a little German.
Okay, shall we
All right.
continue?
Yeah. Go ahead.
Okay.
I think there's only one or two questions.
All right.
Yeah.
I tried to go fast, Ryan, but probably still never go that fast.
It will be
Okay, so I guess that's the end. If you wouldn't mind rewinding back to where we started today, Jerry, and there's the diagram that has the decoder and encoder algorithms with the for loops.
Let's see.
So, yeah, just keep going backwards until you sort of stumble across it. Yep, keep going. It's probably 4 or 5 more slides at least. There it is. All right, so one forward from here, one slide forward. Perfect.
Code?
Yep. Okay. So last week what we talked about is although they tried it where all the different resolutions you predict the image, they found that it worked better when you do this thing that's like XGBoost, where you just keep predicting the residual, the leftover, whatever the previous, iterations hasn't yet managed to successfully predict. And so on the left-hand side here, what you see is this for loop, and it's for however many steps we've designed. And as I shared, that in the paper, they had 10 steps to go from 1 by 1 to 16 by 16. And whether or not you understand all the little details in the middle, but basically they say, okay, this is the encoding. So they say, here's the actual embedding, right? So we take the pixels, we run it through CNN. Here's the actual embedding, and then we're going to use our vector quantizer to round it off to approximate it to whatever the nearest bucket is. And we record what the bucket number is on this queue that we have. And then ultimately, when we've done that for however many, if we're on the 3x3, we do this 9 times. When we recorded that, then we take basically that prediction, which is the center of the bucket, and we subtract that from what the actual values are, and then we're ready for the next iteration. So on the right, the decoding, what we do is we start with the 1x1, and then we run that through our code book, the vector quantizer. Yeah, I see there's something in the chat. I'll get to that in a second. And what we do is we decode that. So we have the bucket number and we turn that into an actual vector. Okay. And then we take the 2x2, we turn that into vectors. And so we're going to do this, and we're going to consecutively sum all of these things up. And then ultimately, when we have the final full representation, 16 by 16, we turn that into pixels. Okay. What the GPT-2 LLM does is line 5 there, the Q pop function. We are not actually going to have codebook values that we've stored from decoding. We're doing generation. So basically what we're training the LLM to do is to say, okay, I'm about to generate a new image. I was told the category is roses. So generate the bucket number for the 1x1. It says, okay, bucket number 5. Great. Now I have bucket 5. Now I need you to generate the 4 bucket numbers for the 2x2. And then it's going to generate 4 tokens, right? And so when you have a word, like we show the word, but really it's just word number, right? It's like word number 5, word number 17, word number 234. And so then it just goes and spits out these 4 token numbers, and then it spits out 9 token numbers, and then 16, all the way until in the very last step, it's a 16 by 16. So it has 256 token numbers that it spits out. And once you have all of those token numbers, then basically you are running them through the code book, you're getting the vectors, you sum them all up, and then you're able to basically get the pixel values. So that's the function of the LLM, is it has to be trained to figure out, based on what it's seen so far, the class ID and the lower res, what are the token numbers for the next higher resolutions. So this is a very specialized task that we're training this. This is no longer a language model. This is very much a predict the next VQVAE bucket number model.
Ted, just to be sure, that is not just the Q pop-up, that's this whole bit here, right? The Q pop, the lookup, the interpolate, the whole 9 yards.
The Q pop is what the LLM does. Everything else is wrapper code around the LLM.
Oh, okay.
So the LLM really only does line 5 on the right. So what you say is, let's say we've so far decoded up to the 3x3. Okay. Your prompt to the LLM, as we're used to prompts, okay, contains the class, the token number for the 1x1, the 4 token numbers for the 2x2, the 9 token numbers for the 3x3. So that's, what is it, 16 token long prompt, right?
Okay.
And so that's your question or your user instruction. Okay. And then basically it's going to do next token prediction. We're going to do them in parallel for efficiency, but you could hypothetically do them one at a time. Okay. And it's going to spit out 16 more tokens and say token 1, token 344, blah, 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 blah. And we get to the 16th one, that is enough tokens to comprise our 4x4.
Right.
still relatively low resolution image, right? And so then when we're done with that, basically what we do is we turn around and we say, now we've got 32 tokens, predict the next 25 for the 5x5. And now I've got whatever that is, 57 tokens in my prompt string, right? Now let me generate the next, whatever it is, 36. So it's the same way as if you had a very short prompt and you said, write a poem, whatever. And then it writes the first line of the poem. Then the next thing it's going to do is it's going to write the second line of the poem, right? And then it's going to write the third line, and then maybe it's going to say, okay, now this is a rhyming couplet, so this has to rhyme with the second line, right? And it's going to keep going until it's done with the poem. Maybe your poem is 10 lines long. In this case, an image is 10 lines long. The lines happen to be variable length. The first line is the really short one, and the last one is the longest one. It's 16 by 16. Okay. But so the trick is this algorithm, in this chat's asking about the algorithm. Remember, they shared code for this. So you can see the Python code for implementing the algorithm on the left and the algorithm on the right, the encoding and the decoding. Okay. And again, if you just took an actual image, you can run it through algorithm 1 on the left, and you'll get a list of bucket numbers. Okay. You can run that list of bucket numbers through the algorithm 2 on the right, and you will get a reconstructed image that's close to your original image. Okay. The trick, what we're teaching the LLM to do, is to predict what the list of numbers will be without having any decoder and any original image. You just say, give me a dog, give me a cat, give me a rose, and it has to predict what that whole string will be. So in the same way that when you say, write me a poem, it could write anything, right? But when you say on the first line of the poem, roses are red, now all of a sudden you've boxed in certain decisions down the road to say that this is the approximate line length and blah, 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 right? And then if you say violets are blue, now I got to rhyme line 4 with blue. So by that same token, if all I told you is I want a dog, once you start giving me some of the initial tokens, like, oh, look, this looks like there's blue stuff at the top. I'm going to probably generate an image that has sky. And oh, it looks like there's a bunch of green pixels at the bottom, so I'm going to say there's grass, that the dog's on grass, right? And then at some point you're like, oh, the dog's red. How many red colored dogs are there? Maybe it's a, what is it, Irish setter or whatever, like, so as you start generating more and more tokens, you're boxing yourself in for later on. And then as you get to medium resolution, it's like the dog's head is on the right, the tail's on the left. Everything I generate higher res now has to be consistent with that. And so each time you generate a new resolution, you're effectively locking in certain information. Is the dog standing? Is the dog lying down? What color are the dog's eyes? Is the dog's mouth open or closed? Is the tail up or down? You know what I mean? Like, and so that's kind of the idea is if you imagine this low res thing slowly coming into focus, you're committing things just like, it's not exactly the same, but it's just like as you write a poem, you are starting to commit things for the future. You can't say roses are red and then the next line is 50 syllables. That just would be a very weird poem, right? And so you can't have the dog start to be red and then all of a sudden change your mind and decide that, nope, the dog's going to have 2 heads, one on the left and one on the right. You've locked yourself in. The dog can only have 1 head if I'm making a realistic dog.
Yeah, this is kind of how I paint. I don't know how other people paint, but you have this like general structure and then you put in the detail as you go along. At least that's what I'm kind of getting out of this, right? You and then start locking in, if you're painting somebody's face, they're looking to the left or they're looking to the right. And, you paint the oval first and then, you decide where to put the eyes based on that assumption and things like that.
Yeah, and it's not a great analogy, but like my daughter writes, and so sometimes she'll have characters, and only at a certain point does she realize there's going to be a scene where the two of them argue. But she didn't know that writing the first sentence of chapter 1, right? And then even then, once she realizes that they're going to argue, she doesn't know the exact words they're going to say until she kind of like gets there, right? So it's a little bit of that. And I think that's the magic of autoregressive stuff, is that
Right.
You don't have to at the very beginning know absolutely everything about the dog that you're going to generate. As long as you start generating things that are somewhat reasonable, if you in the early steps somehow had the top of the image being purple and the bottom of the image being orange and the middle where the dog should go being, I don't know what, green, like it's going to be really hard to come up with what on earth, realistic image would fit this, If you actually ever did this and were mean to this model and forced it to do that, it would probably end up, I'm guessing, it'll come up with like, a dog where the owner dressed them up. And so they're going to have a green sweater on because I don't think there's any actual green dogs, right? But so you can imagine there's like some corners of the distribution where like that's plausible. And so probably that's the direction it'll get pushed into because it's been trained on what's plausible for the different, kinds of things. Yeah, Jane?
Yeah, so the output tokens are it's still a distribution, right? So if you're doing like a 4x4, it's like 16 distributions over the token IDs. And then so you can apply, greedy, whatever algorithm to like select your 16.
Yeah. So you can sample any way you want. So like when you ask it to write a poem, you could always just take the highest likelihood token from that distribution. Or you could decide you want more creativity. So you're going to sample and you're going to allow a certain chance that one of the lower tokens got picked. Okay.
Right.
So in the same way you would do that with word tokens, you could do the exact same thing here with picture patch tokens to say, if you did absolute greedy, then I think if your random number seed is the same, you always get the same dog picture over and over and over and over again.
Right. Yeah. So that's interesting because then it's like, if you sample differently, you pick the second best or whatever, and you could end up with different sets of images from the same.
Yes. And if you notice the default for ChatGPT, whatever other language LLMs, it's not to do zero greedy sampling. But when you read an academic paper about it trying to solve a math problem, they always use greedy zero temperature sampling because there they don't care if the answer is boring and repetitive and wooden sounding. They just want the right answer.
Yeah.
But it wouldn't work for generating a poem or other kinds of things.
Yep. Cool. Thanks.
Ted, quick questions. See if I'm understanding this correctly. The image is in a continuous space.
Yes.
What would it be? Just the function E? The encoder function maps that to a continuous F.
Yes, so that's a CNN that maps it to a 16 by 16 by some number of channels,
right?
A bottleneck. Yes.
And likewise, on the other side, line 9, the decoder takes a continuous F and maps it into the image space. So
yeah, it's trying to reverse the CNN, so it just goes back to pixels.
So I guess I've typically thought of quantization as kind of this space savings type of thing, but am I interpreting this reasonably that the Q function, which goes from a continuous space to a token discrete space, that's actually mapping from continuous to token space to discrete space? And
It is what you said.
vice
It is just
versa.
a space. It is just a space saver. Um,
Well,
it's rounding, right? It's a
except you have
um.
discrete. You have to get from continuous to discrete to use the language model. So
Yes.
the Q is mapping from continuous to discrete, and then that phi sub k is mapping from discrete back to continuous.
So the Q is really doing two steps in one. Okay. The Q is mapping from continuous to continuous by picking a bucket that it goes in. Okay. So it says I have
Oh,
4,096
So that's a
buckets.
bucket number.
What's that?
So it's discrete when it comes out. It's what bucket number you're going to be.
The bucket number is how it gets discretized. It
And
would
that's what you
still
do.
be compressing, shrinking, or whatever if it only did the rounding part and didn't do the discretizing thing, right? So if Q returned the center of the bucket, right, then that would still be continuous. But instead, by saying I'm going to use a code book, I then
Yeah,
get to discretize it and represent it
right,
as
right,
just a bucket number,
right. And then
right?
what I was wondering, so that the inverse of that, the phi k, is going to map from a discrete token space back into a continuous space F. And I'm guessing that that sub k means that it's a different mapping at the different depths. Is that right? So
Yes.
I'm kind of imagining that um, in the first layers, I have the big numbers, but I've got this little residual left over, and then I can add a little bit more at each layer to kind
The,
of
the
find.
vector quantizer knows what level you're at when
Right.
it's quantizing. In theory, it could just decide it's going to do the same thing at every step,
Yeah.
but it probably does something slightly different.
Yeah. Okay. Cool.
Yeah. So the idea is you hit the nail on the head. It has to be discrete because we have a fixed vocabulary size in any LLM. Now, language ones, it's bigger, 30,000, 50,000, 100,000. In this case, the vocabulary is only 4,096. But we have to have a discrete vocabulary, and we just train it on a bunch of sample strings. So, you give it strings from Wikipedia, you give it strings from Harry Potter, you give it strings from scraping whatever websites off the internet, and eventually it learns the patterns of those strings and it learns sentences and nouns and things like that. And that's all they did here is they just gave their GPT-2 lots of examples of images. And eventually it kind of figured out the pattern that like, oh, if you said dog, and then here's some of the low res information, I can kind of figure out what a realistic high res completion of that would be. If you said rose and you gave me these low res tokens, then I can kind of figure out what the high res probably is a realistic version of that. And I don't remember what all the ImageNet classes are, but soccer player, whatever. Eventually, it just learns how to complete the pattern. It just so happens these patterns aren't sentences; these patterns are images. If you used a very simplistic encoding of the images, to turn them into tokens, this technique would still work. It just might not work really great. It would work on some level, right? If you asked it for a soccer player, I'm sure you would get something good enough that if you looked at it, you'd say, that's probably a soccer player. It's definitely not a dog. It's definitely not a rose. Okay. The trick to this paper versus that paper versus whatever is we want it to be really, really good at generating images. We want them to be really high quality. We want them to be really realistic, you know, and like that. And so that's why they need a very fancy VQVAE in order to turn your pixels into tokens. If you just did it the really, really dumb way, it'll work. If you just do one step, vanilla just did it. Work. So from here, the thing that we can kind of talk about is that This was the first baby step with this technique. And so when you're generating the very, very first prompt, the input is a single token which told it which of the 1,000 ImageNet classes that we wanted. There was no text. You couldn't ask for an astronaut riding a horse, okay? ChatGPT, clearly you can ask for that, and you can ask for things that are very detailed. So it's proprietary. They're being very hush-hush about it. But you can imagine that if you train ChatGPT so that the language and the image parts had shared knowledge, then if you give it a much longer prompt, probably a whole lot of system instructions in addition to, I want a picture of an astronaut riding a horse. Then when it's going to output that very first token, which is the low-res 1x1 image, instead of now just knowing you want a dog or you want a rose or you want whatever, now it has a whole lot more information that it can attend back to and think about and say, what should I do for my very first token? The way most text-to-image generation models work is they take that text and they embed it to a fixed length vector. And then that vector goes into attention with the whole image generation process. But you can see that as soon as I say the word fixed length, we're kind of in trouble. So maybe you can tell it that you want an astronaut riding a horse. Maybe you can tell it you want a teddy bear dressed like this, doing that, or whatever. But when you get to some of the stuff with ChatGPT, where it's like, I want a 6-panel storyboard. In the first panel, this is happening, and this exact text, this full sentence that's 13 words, needs to appear in a bubble above the character. And then in the second panel, I want this. That is way too much information to pack into a single, a single fixed length vector of the kind, the short kind that people have been using up till now with Midjourney and Stable Diffusion and all of that. And then not only that, you do this and it generates an image. And then you say, I kind of like the image, but the font that you used on the storyboards is kind of boring looking. Can you change it to a more handwriting looking font? And now you want everything about the image to be the same, except for the font that the letters appear in. So you want the characters to look the same, be in the same position, be, whatever. You want all that. So now you've got to really attend to an even longer context because you have all of the system instruction, all of your original instructions, some kind of intermediate information about what image it generated on the first pass for you, and then your follow-up instructions saying, change this one thing, change the font. So it seems plausible to me that that's why it takes so much longer than Stable Diffusion. It takes like 60 seconds to generate an image because it's got all of that stuff that it's got to attend to when it generates the first image token. And then it has to attend to all of that plus the first image token when it's generating the next 4. And then it's got to attend to all that plus those 5 when it's generating the next 9, and so on and so forth. And we don't know how many, like, did they use a 16 by 16 or did they use something higher resolution, right? Maybe they ended up using a, whatever, 64 by 64 internal representation. And so then what's 64 squared? I don't know, 65,000 or something like that? No, that's too big. 16. I don't. Confusing myself.
2 to the 8th?
No. But my point is that. Maybe? Thank you. So that itself is getting longer. Plus, it has all of the previous scales, right? You start adding all the squared numbers 1, 4, 9, 16, 25, 36, right? Things are getting right. So you can easily see where it might have thousands of tokens that relate to the image, plus however many hundreds, thousands of tokens that are in the image generation prompt, as well as your particular text, that you said, the whatever, storyboard about an astronaut riding a horse and blah, 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 blah. So we don't know, but I hope that makes sense as to like how one might extend this particular technique from being just give me a class to let me give you text and let me have crazy high resolution images. So I don't know that we've actually shared some of the images, but like, I was pretty impressed with the images in the OpenAI announcement. So if we want, we can kind of take a look at that, switch over to that. But you'll see there are ones that have maybe more than a dozen sentences on that. And like most of my experience is if you give an image generator 2 words that you want to appear in your image, there's a decent chance at least one of those 2 will be spelled wrong. And this is just like crazy orders of magnitude better text, better fidelity.
Ted, do you know a URL we could look at to see some of these images?
Let me find it.
So we've been talking theoretical. Might be nice to see the end result.
I actually had a little bit of the opposite result. So I downloaded the source and used the D30 weights. I think that 2 billion. And I was kind of surprised that the quality, across the panel of 16 of them, there'd be a couple of good ones, but quite a few not so good.
Sorry, Roger, which image generator were you using?
Oh, I thought we were talking about the VAR.
Oh, no. So now I'm talking about the current chat GPT stuff from OpenAI that we don't know.
Gotcha. Sorry.
But we think it might be based on VAR. So I put it in the chat, Jerry, if you want to, since you're sharing your screen, if you want to switch to that.
Okay. I am having a problem. I don't know why I'm not seeing the chat. Damn it.
Oh, just because you're...
Because I'm sharing probably.
Do you want me to send it to you another way? Slack or?
Yeah, you can just Slack. Do it in Slack. Thank you, sir. So this is this open AI index thing, right?
Yeah, just there.
Okay.
Whatever. Blog, announcement, promotion, whatever you want to call it.
Introduction to image generation, blah, 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 all that good stuff, right? So
Yep, you're still sharing YouTube, so I don't know if you need to.
Yeah. Well, what I'm gonna do over here is I'm just gonna put it in this tab.
Cool.
Okay. If I could copy it, damn it. Copy link. Oh what is going on here? No, that's not it. Okay, copy the link. Now go to the link. No? Shit. Sorry. For some reason, it is not letting me copy this darn thing.
Well, you know what? You could just do this search if you want. Just
Okay.
say OpenAI image generation.
Just right like that? That's sufficient to find, do you think?
Probably, yeah.
All right.
Yep, there it is.
This one?
Introducing. Yep. All right. So yeah, so you look at that first image. It's someone writing at a whiteboard. And I don't think in the prompt they specified all of the text that was going to be on the whiteboard. Okay, so they didn't specify each and every one of those words. But I think what's impressive is they asked for a second image with the two people doing a high five. And if you look in the background, I think all the words in the background are still the same.
Yeah.
I'm not sure if the position of the letters is exactly to the millimeter in the exact same spot on the whiteboard or not.
Mm-hmm.
But that is a significantly high degree of fidelity between the two images for what's
Well, the interesting thing is too, it even got this, reflection, if you will, correct.
They asked for a reflection in the prompt.
Yeah,
They said,
yeah, but
someone
I'm
writing
just
on a
saying,
whiteboard, and in the reflection we see the bridge.
Yeah, but it even got the fact that these two are now their shadows are occluding part of that reflection.
Yep.
That's yeah. The fact that this is generated, I think you'd be hard pressed to say this is a generated image versus this is a photograph.
Yeah, this is very photorealistic. All right, so you can scroll down, and some of the other ones are just very pretty images. A handful of them do have text in them, which is one of the things that I found most notable.
Character consistency.
The character consistency that you can actually say, generate an image to me of a cartoon, blah-de-blah,
looks like a penguin
tiger,
wizard
blah, blah, blah.
there. Yeah.
Yeah, and then you can say, now give me a new, completely different scene where this character is at a table, eating pizza, and now give me a brand new scene where this character is in an office at a desk, and so that's the kind of consistency that you can have, which is very impressive. Oh, I didn't mention so the one with the whiteboard also, although in the first one the gal's sort of facing away, you can't really see her face, but her hair and everything else is relatively consistent to the image below.
Yeah, it is. If you look here, there's kind of a wispy piece here, and here it is in this one here on the lower one.
Yeah.
That is, yeah.
And then if you ask for another one where you could see her face, now the expectation is it'll actually be consistent. It's probably not going to be perfect, just like, not Hollywood quality, but still compared to what we've had in the past, it was just, it was so much work if you just got an image you liked and you wanted a second image of that character doing something else. So hard to get that. Yeah,
and the uncanny valley is almost gone in some of these too.
Yeah,
that's impressive.
Yeah. Not all the images are photorealistic, so you can scroll down.
Okay.
I particularly liked this next one here, the witches and the street sign. So again, I don't think in the prompt they specified all the wording that was supposed to appear on each one of the signs, but the fact that it just had to come up with a bunch of realistic wording, and they spelled everything right.
Yeah, but it's interesting, because they had the I associate witches with brooms, right? And the magic carpet bit, and The
Yeah, I don't
reindeer,
associate witches with flying carpets, but at least it's spelled flying carpet or whatever correctly, and
right, and then even on the reindeer parking, it got kind of the dates correct too, right?
yeah, yeah, exactly. December, whatever that says,
24th,
24th through
25th,
25th.
yeah,
Yeah.
yeah.
So there's a whole lot packed into it, even if the user didn't specify every single word
Now,
that should go in there.
if we do the read more, is there more context here, or is this
I haven't looked. Yeah, yeah. I think there's a longer prompt.
Let's do that. Random. Okay, so this actually spelled this out.
Oh, so they really did say like
Yes.
here's
Yeah. So here's your context, and here's your
yeah.
characters. Obviously, those must be some sort of vocabulary meta words or something.
Yeah.
But it actually did it correctly.
Yeah. So again, that's a very long amount of, I wanted to say at the bottom of that reindeer sign, violators will be placed on the naughty list.
Yeah.
And it did
Yeah.
it, and it spelled it right. And it remembered it,
Yeah. Yeah. So my fallback career of going to stage photography is kind of going by the wayside here.
Very rapidly, yes.
Very rapidly, yeah. Wow, that's a whole genre gone away. What else do we got here?
So they took that cat that you see on the upper right, and they added the monocle. They added the funny. I think it's supposed to be like a Sherlock Holmesy kind of a.
Yeah, but they figured what a detective hat is based on something there,
Yeah,
and a monocle.
and then somewhere below, we're going to take this cat and just go an order of magnitude more. I don't know how much you have to scroll, but basically it's imagine a fake screenshot from a video game where that cat is the protagonist. And
Yes.
so you've got the menu, the little icons on the left, the active quests text on the right.
Wow.
And this is just a series of iterative prompts, all starting from that one picture of the cat that we saw up there.
Right. So this is a video game. Wonder what these look like here. Concrete poem. Concrete poem of luxury eggshell texture card.
Yeah, if you say read more, did they give it all the text, or did it also write the poem?
Well, yeah, it is starting with that OpenAI, from the first cave painting. Yeah, that's here. So it looks like they gave it the text.
Okay, that's a lot of text for it to remember to stick
Yeah.
into an image.
Yeah, and with new capabilities, blah, that's here, down here.
Yeah.
So
I don't even know. Is that a light bulb? What is that? I don't know. But the point
kind of
is
looks
that
like a light bulb to me. It doesn't. Did the prompt say? No, it didn't. It said concrete poem on luxury eggshell textured card, so it's eggshell colored, but nothing says put it in the shape of a light bulb.
Yeah. So that's what it came up with for the concrete poem, Bart. But
Let's see the sticker.
yeah.
Can you make a cute minimalist raccoon eating a strawberry sticker? Use a thick border and a transparent background. Okay. And then do a minimalist one with try a different minimalist style and a gray raccoon. Interesting, it still kept the concept. It remembered the strawberry too.
Yeah.
Can you put chew marks on the strawberry? Maybe some red mess around. I'm just looking at graphics people standing in the unemployment line now.
Yeah. So I haven't tried it, but people have talked about, let's say you have a picture of your product sitting on the kitchen table, right? So they say that you can say, okay, take that picture of the I don't know, whatever coffee machine, right? Remove all the background, Now take that coffee machine and put it in this scene with these characters and blah, 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 blah. Right. So that's something that, it would take sort of like a bunch of Photoshop and a certain, skilled design person historically.
Mm-hmm.
Um,
Visible elephant. Let's see here. So here, look at this. It represented, this third line says square root of 9 is equal to 3, and it got the square root symbol in there.
yeah.
And same thing here in the, b equals
Yep.
plus or minus blah, 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 4 you see for the
Yeah.
other
I would
stuff
not
there.
be surprised that ChatGPT knows the math, whatever you call that, the equation formatting. I don't think this is LaTeX. I don't know what it is. But anyway, I'm not surprised that it knows that, but that it now has been able to make the leap to drawing it in a, like the plus minus thing and the square root. Like those are not crazy hard, but they're certainly not trivial. They're not kindergarten things to say that I want to screw, and it's a giant fraction, so you have to decide how big the horizontal line is.
Mm-hmm.
So yeah, it seems like there's just a ton of world knowledge that kind of is already baked in there.
So it said design a vehicle with triangular wheels. Oh, and
and then I think they
this
had an image that they gave it to say that it should be in the style and inspired by this image I
right.
uploaded.
So it had to then infer from these images that it should be on this sepia tone or whatever you call this background here,
mm-hmm. Yep.
and all that, and this was this style of turn of the 19th century type thing. Or,
yep.
Wow.
So if you had friends who were sending you, pictures that they turned into the style of Studio Ghibli, that's where this came from. Is you upload your photo and then ask it to give it a certain style.
Oh, now put this photo into New York City.
Yeah. So you see, there's so much faithfulness from the drawing that was the sepia card to now photorealistic.
Yes. Yes.
That level of consistency is, to my knowledge, nothing we've seen before.
Well, maybe AI will take over all the jobs. All we have to know is use these tools.
Yeah, I was saying to folks at work, it's not going to be too long before instead of a bitmap, it can give you encapsulated PostScript. And then, then the sky's the limit for you to, really blow it up big, make edits, whatever. Yeah, I liked this one. So there's a lot of text in terms of the ingredients,
Interesting. It is not giving it the recipes.
Cool. Yeah, like you wouldn't be surprised if ChatGPT text only knew the recipes, right?
Yes.
But now it needs to use that level of recall to put the text onto the cards. And it also needs to know what shape glass makes sense for each drink.
That's
and
true.
What color each drink will look like.
Yeah. The margarita is in a margarita glass. The mojito's in a glass that you'd expect to get a mojito in, so on and so forth.
And the martini's in one of those triangular ones.
Yeah, a martini glass, right? We call it a martini glass. I know that.
Yeah.
Yeah.
Wow. So again, some of this marrying of the ChatGPT strengths, but now with images. So, what does Karl Marx look like? Now let's just place him in a, front of a wall carrying a bunch of bags.
And it actually got the letters spelled correctly, didn't monk them up. But it, glancing over his shoulder, startled expression as he tries to avoid being photographed. So it even got the fact, oh, he's being photographed, therefore, yeah, okay, there's a flash. Oh, I guess it gave him the flash glare type thing. But it even got, here's his shadow, and his shadow is behind him because the flash would be coming from the side they picked.
Yeah, and I feel like the flash glare and a little bit of the f-stop, the slight blurriness of the cars behind him. I mean, it looks pretty good to me.
Yep. Wow. Well, we could spend hours going over this thing, but we are coming up on time. So if you had more, Ted, or is this pretty much it for tonight?
That's pretty much it. Any questions? So again, they haven't published exactly the technology, but they said it's autoregressive, that it's not using diffusion. So it seems like some extension of this VR detection. And there's other papers. I haven't managed to fully deep read either the Infinity or the XAR instead of VAR paper. They're all coming out of ByteDance.
Great. Well, cool. If nobody has anything else, should we finish it up for tonight then?
Yeah.
I have one question that might be redundant.
Go ahead. What do you got, Joyce?
I arrived late because I came from another thing, but I'm just staring at that codebook stuff, and I just want to I can't figure out from looking at it, is it really just one codebook? So no matter what resolution you're working at, it's going to quantize that vector, because you've got the same channel dimension, I guess, at all times. So it's always the same space in terms of dimensionality, but is it always the same codebook that will map that C vector, the channel dimension vector, at any position at the current resolution? Yeah, so if you look at, Q of interpolate, so F is the image, it's been encoded to a feature map. F stands for feature map, I guess. And then HK and WK, that's the working resolution. So we sort of resample to that resolution with interpolate, right? And then we go through the quantizer. Is that always the same codebook quantizer for everything?
It is. We let the VQVAE learn which 4096 entries it wants to have in its code book, but it is stuck using that set of 4K for all resolutions.
Mm-hmm. So I guess it can sort of redefine. I mean, in some sense, it always knows what resolution it's at. So in some sense, it kind of has that information as side information. You can think of it as appending in some sense. But yeah, it just kind of surprised me. I sort of intuitively expected it to be a separately learned code book for every resolution. But no, it's one code book, 4096.
If you were building, Whisper, for example, you would give each resolution a unique code book, and it probably works slightly better than if you force them to use the same one. But in this case, the whole goal was to be able to send it to GPT-2 and have it predict the tokens, and so it has to be a single fixed vocabulary.
Okay, great. Thanks. That clears me up.
Yeah. So residual vector quantization does not use shared codebooks normally.
Mm-hmm. Mm-hmm.
Just like you were saying, it's not intuitive. I think it's slightly different because residual vector quantization, I think you tend to be actually capturing different information. I think naively, perhaps, I think of it as the first pass is going to get more low frequency information, and the later passes are going to get more high frequency information that are of different amplitudes. Okay. Mm-hmm. In an image, I do think you may be going from low to high frequency in a sense, but I think the amplitudes are more the same. So grass has a lot of high frequency, information about the details of the individual blades. but I don't know that the amplitudes are any different than the low frequency information.
Yeah, they're just encoding, so they're just symbols. So I guess there's no notion of amplitude in the feature space exactly.
No,
It's-
but I'm saying implicitly, if they were different amplitudes, then this shared codebook might not work so great.
Uh-huh. Mm-hmm. Yeah, I really have to think about what it can do. That's, it could just partition the set of vectors, the set of labels. It'd be interesting to see how the distribution. It'd be fun to see a histogram of the codebook quantizations as a function of level. Just kind of plot them all. So I've got the code.
Cool.
Cool.